what's to come.
Okay.
We are dealing with quantum model of the atom. It's one of my favorite units to get to. It is really cool. So we're going to deal with this, but there is a question that comes around. This question was asked in the early 1900s. What is light? Now you have to understand where this is kind of going. So everything was based around, we could start categorizing things. Physics was imagined to have been almost completely complete at this point in time. They look and they say, we know almost everything about everything, we just got a couple cracks that we need to fill. But we're pretty solid. It's pretty impressive. We're like, wow, we've almost known everything of everything that there is to know in physics. Excellent. So then, everything can be ranked and broke down into two categories. The categories we got was a wave or a particle. And whenever we would look at these things, you could categorize things as them. Perfect example, you're at the pond. You take a rock. What would you categorize a rock as? A wave or a particle?
Particle.
Particle. Bingo. Yes. Now, you take said rock, you look at the water, you look at your beautiful significant other, you're like, I'm going to impress them. You take that rock and you yeet that thing as hard as you can.
Not
And
skipping.
it hits the water. Yeah, no skipping. We're just yeeting.
Just bit plunk.
Yes. Okay, you got me? Okay. Yeet that thing out there. It hits the water and goes bloop. As it goes bloop, what do you see?
Light.
Oh, wait.
Rippling out, right? So these were the different classifications to it. So when it comes to light,
Can you make a sound effect for the lights? Thank you. I needed that. I didn't need that. I can envision it now.
So this is where the whole question comes down to. What is light?
I thought he was gonna mess with us. I thought, what is love?
Baby, don't hurt me. I'm sorry. So what is light? Very interesting.
Thomas Edison created that.
Thomas Edison did not create it. You're thinking of the light bulb,
Which is light.
which emits light. It's not light.
I think.
I think David's right. David has the answer.
So here's the question.
Jesus definitely created light.
No, that was gone.
Yeah, you're right.
It was not Jesus.
So I have a question for you. What is light? How many of you look at me and say light is a wave? Raise your hand.
I think it's neither.
I think it's
both.
How many of you think it is a particle?
No, it's neither.
It's both.
I'm down.
How many of you are just not going to vote today? Appreciate the honesty. What makes you think both?
Well,
I can do
I
both.
said neither.
I think it can be both because
I said both.
I think this is all going to explain to us.
I'm
But
going to explain.
I think like the waves hit your eyes, they hit your eyes.
The waves. So light is a wave.
And it hits your eyes.
All right. Lasers.
Lasers.
Lasers are
Light.
light.
Yeah.
So there's a natural thing that occurs with waves. You see it whenever we yeeted the big rock whoop, into the pond and the waves radiate out. What happens to the wave? They keep
They get smaller.
going and getting smaller, which is expanding. So they're expanding. So waves expand. So if you look on the board, you see my small little dot. Now watch. Same thing, no magic tricks.
It ain't expanding. Oh, it's expanding.
Oh.
Now compare the size of the dot.
Don't say Jackie's go.
He's messing up. Oh no, I thought he was messing up. I thought, I'm so
Nope.
stupid.
So what happened with it?
It expands.
It expanded.
So,
So we would classify light as a
Wave.
wave. So we know that light is a wave. That's a simple reason. So this is where things got interesting. So we think we have everything figured out. So we know that light is a wave.
But it's also a part.
Like bingo, bango. Why?
Because it has to be emitted from the point. Like, you gotta have light to be emitted from the sun or a light bulb, and that in itself would be a particle.
Just stop.
got my boy TS.
So here's what brings us in to this. You need to know what parts of a wave are, what waves look like, how waves operate. Because you clearly can see that light is a wave, so now we need to know what's going to happen with waves that are interfering or these just doing different things. Other
Trying to
things.
be different.
So let's look at a wave. It's definitely a bar graph. For those of you who are in trig,
This is calculus.
trig function.
What's wrong with that?
You're doing that in calculus right now.
Calculus has curves. Trig.
In your trig class, you never graphed a function. It's a trig function.
Yeah, but like, that's a sine function.
It's more sharp.
Yeah.
So just calculus.
Trig.
Yeah. Calculus.
Or you're a chemistry teacher, you're obviously more about math.
Alright, so whenever you look at these parts of the wave that are important, because you have to understand parts of the wave to understand how we're going to measure waves. So the first thing you're going to look at is, anybody know what the top peak, the very top is called?
The A.
Well, nice guess, but no.
Had to be close.
Stop saying these.
I bet some of you used this morning. No?
We used this morning.
I guarantee it. It's, for me personally, I'm not a huge fan of the toothpaste, but I do like the mouthwash.
Toothbrush.
Don't brush all day.
Colgate?
No, I do.
Listerine. It's
Listerine.
Come on now, tell me Listerine. Crest. Oh.
Correct.
Say Colgate.
I don't like Listerine. Listerine is like all like ignites my mouth on fire, and
That's the
it.
good part.
I know how people think. They're like, I feel the burn. It means my mouth's getting clean. But if my mouth can get clean without a burn,
That's why
I'm gonna get clean without the burn.
That's why I just fish with bleach around the mouth.
Feel the burn. And then you got the bottoms. It's the very low points of the waves. So you know what they're called?
Top is a crest. You guessing the bottom is a crust.
Very nice guess, but
I'll
no.
take sad for
Pigs like to eat out of these.
Trough.
There's a trough.
Bro, you're
Good
supposed,
time
to
there.
have, you're supposed to have the calculus in the truth term, so you don't know the bottom and the top of the graph.
So when you look at this, the crest is the very top, the troughs are the very bottom. Well, why in the world do we care about this? We care about this because of things that we look at, and it comes in terms of discussing the wavelength. Which is the length of a wave measured from the same If I wanted to measure the wavelength, you have to go from the same point to the same point. So I have to go from crest to crest. That is a wavelength. It doesn't have to be crest to crest. It can be random point to random point, as long as it's the same two random points. It can be trough to trough. This is the whole thing we're looking at, man. Now you break it down and you look at the frequency. Frequency is how often a wave passes a certain amount of time. So you look at frequency, you would choose the certain point on the wave and you would start measuring from there. So if I measured from the crest, it's every time a crest would cross by, I'd count it, and then we would divide it out by the certain amount of waves in that certain allotted of time.
Dakota, Dylan, and Lily Sansom to the office. Teachers, we will be sending students down to the play a little bit later. We'll be going to grab and go first, and then we'll be going to the play. We need you to collect each student's $3 in the classroom. Send us a list of the students that paid along with the money to the office. Thank you.
Roll my money. Also, listen, you
Bring
know,
in my money.
remember for homecoming week or whatever, we're supposed to do crazy sock day or whatever for one of the days? I was on Amazon. I was on Amazon and I ordered a pair of socks that you can customize the photo of. And I was going to use that photo, no, one of those photos as the thing on the sock, but it wouldn't have came in until the 15th. It would have been way out of time, so I didn't.
Should have used some express shipping.
Expression, dude, I have.
Okay.
Probably won't help.
They really just love
Why are you sad now?
to interrupt. Because now I have to collect your money.
I know.
You got some cash?
Somebody give me
Yeah,
my
you-
Good.
I don't get to leave. So,
What? Just take my money. I really need to see that play. I've heard great things about it, left some great reviews. Well, I haven't left it, I've seen some great reviews that haven't.
I'm going under the impression that they meant to do that third period.
we did.
Okay.
All right. So this is about the wave. Okay? So everybody looks at this point and goes, all right, man. Light's a wave.
Maybe not.
It's neither.
Which then brings us into a
It's
question.
just like,
Because then scientists started wanting to look at things and say, well, okay, cool, man, whatever you got to say, fine, whatever. Then scientists started looking and saying, what is an electron?
that's part.
You ever think sometimes just scientists ask too many questions that nobody cares about?
I think I just.
Lots.
So you're a factor in this class, no? So you look at an electron, what is an electron? Especially since the fact you like using your cell phone, no. Because if it wasn't for these questions, you wouldn't have your cell phone.
Science could have been covered in fourth grade. didn't it?
So what is an electron?
A negatively charged subatomic particle.
Good job. negatively charged
String theory, 12 years old.
subatomic particle You know my favorite idea of string theory is how easy it is to mess with somebody's head.
God, it's so easy.
Do you know what the summation of all the integers from 0 all the way to infinity, so 0, 1, 2, 3, 4, 5, 6, all the way to infinity is equal to?
I probably couldn't care.
Probably
Negative
infinity.
1/12. Exactly. Everybody's response.
I was gonna say it was probably infinity, but
Nope, it's negative 1/12.
why?
String theory, man.
I don't like it.
It just is. There's like a simple breakdown explanation behind it, and I'm like, holy smokes, that works.
What's the simple explanation?
There's like 3 different summations, and you had to combine them together. But there's like a very complex reason behind why. And then someone looked and said, so you tell me if I took 0, 1, 2, 3 all the way up to a googolplex and added it together, it's equal to negative 1/12. They said, no, that's equal to a really big number. We're talking infinity, you never stop. And everyone's like, it don't make sense. It's like, we know it don't make sense, but it is what it is. It's the truth.
You're so cool.
Alright, so negatively charged subatomic particle. But then there was a problem.
Here's the problem.
There's always a problem.
Hopefully none of you have observed this
All the
before.
lead scientists are dyslexic.
No.
So they've just cooked the entire category of science in general.
Has anybody in here ever put a piece of metal in a microwave?
I have. I put a fork in it, but it was
What did it look like, David?
buoy. Like a lot of like sparks and stuff. Like,
Yeah, give us more detail and more sound effects.
okay, the microwave is going warm, and then
Actually, I put pop
Do you get any sparks flying off?
and then I went, ah! And opened it, and then the little annoying beeping sound. I need to do the beeping sound?
Yeah, it's okay. So here's the question, David. Here's our big question for you, okay? David, did you get a bunch of sparks?
Yeah, there was quite a few.
Quite a few? Did you
I
get
didn't bother to count.
Which is interesting.
You get your noodles.
Well, the noodles didn't burn. Yeah, I eventually made the noodles.
It's all that.
Here's the interesting thing. What is light? Light is classified as electromagnetic radiation. What is a form of electromagnetic radiation?
Microwave.
Microwaves. What do microwaves emit?
Radiation.
Food.
Microwaves. That's why we call them microwaves. If you want to know how microwaves are working, microwaves go in, excite the water molecules within the food, and that's what heats it up. So that's why if you put your mac and cheese in the microwave without water in it, you burn it. There's no water. So, yeah.
What happens if you just stick a fork into the mouth?
Like
It's a very shocking discovery.
I think I should do it.
The results may shock you.
All right.
I thought it was
Here's the interesting part that happens. Electrons are particles. Radiation is wave. But then if I put a metal fork into my microwave and I turn it on, I get a bunch of sparks. What you're seeing with the sparks flying off is electrons flying off. So that brings up the question, how can a wave interfere with a particle?
Some monster energy, a lot of passion, love to be.
Here's the interesting thing that will take place.
So you have a rock sitting on the beach.
Yeah, not like,
Blades coming.
if you got a fan, I mean, sometimes you can push like paper and stuff, paper being particles with the fan.
Feel like that Fortnite email anyway.
So waves of electromagnetic radiation
Oh my goodness, it's done.
interfered with particles. Showing there must be something more.
To be continued.
Something more we refer to has a very special name. You guys are familiar with this person without even knowing you're familiar with it. This person never imagined this is the reason they would have ever got their Nobel Prize.
Rosa Parks?
Definitely not.
Yeah, because she got
Did
it.
she not win the Nobel Prize?
What is this?
No, she won.
Joey, that's. Can't think of
Albert Einstein
it.
came up with the photoelectric effect. Explaining how electromagnetic radiation is a particle
It would be really cool to be a scientist and get into some of the stuff. Discovering things that.
called a photon. That could interfere that could interfere with the particles. It's changed the whole game. Here's the reason why it changed the whole game is to this point
McKinley Sparks to the office.
everyone accepted the fact that the electron was a subatomic particle, and everybody accepted that electromagnetic radiation was a wave. But we couldn't explain the interaction between the two. So now brings up the question,
Why is a photon? You're gonna just throw that out there?
what
Is light.
is light? So light is electromagnetic radiation. So we look at it and we want to know, what is it? Is it a particle or is it a wave? Well, you have something that tells you it's a wave, but then the photoelectric effect shows that it's a particle. So what's the natural conclusion to come to?
For both.
It's both,
How can something be both? Ain't nothing both.
except for light.
It's one or the other.
Because the electrons are particles. Electromagnetic radiations are waves.
Light is waves and particles.
I was right since then.
No,
You
you
gotta
were
explain why.
actually the opposite.
I just knew.
You said neither, you were kind of the
So
opposite.
here's the reason when you look at these, how can light be a wave and a particle? It has properties both. The perfect example of this is looking at the photoelectric effect. Photoelectric effect. I take a piece of metal. On a piece of metal, there are electrons just hanging out. And then I decide I'm going to put it in a tanning bed.
Tanning bed.
Yeah. Because what's in tanning beds?
Radiation.
Light, waves, particles, people,
They tell you tanning beds are bad because tanning beds can cause
cancer,
what type of cancer?
skin cancer,
So you can get skin cancer from it because it
Radiation.
uses
radiation, microwaves,
Heat.
gamma rays, ultraviolet rays, color.
UV rays.
I was trying, man.
Yeah, I know, you just keep throwing out random
Which is
words.
ultraviolet rays.
Okay? So UV rays, which are ultraviolet rays, come in. Whenever this happened, well, let's say it has happened, something interesting takes place. Electrons start shooting off. This was, and still is, the photoelectric effect. Light interfering with a particle. Particles getting shot off. Yeah?
Is this an example or is this actually how they found out? Like, about the other day? They probably couldn't make a tanning bed.
It's just an
themselves.
example.
Okay.
Like they were taking pieces of metal and they could shine light on it and it would shoot electrons off. I'm not telling you if you went home and took aluminum foil and threw it in your tanning bed, you're going to see electrons pop off. I am telling you that unless your like silverware has a specific coating on it and you throw it in the microwave and you turn it on, then yeah, you're going to see some sparks fly. Right, David?
Yeah.
I want to do it now.
Mr. Hall has no responsibility for whatever you do at your home with your microwaves. That's between you and your parents.
My mom won't care.
I got a feeling she's going to care very much. This is what's taking place. Now, listen. I threw a lot of information at you. You have to understand something, especially with the quiz coming up on Friday. You need to understand and be able to explain parts of this. Okay? Come tomorrow, there's going to be a lot more focus on the whole explanation aspect. So before we get out of here, what I want to look at hey Siri, make me a reminder for tomorrow at 6:25 a.m.
What do you want to be reminded about?
Bring French press.
Okay, I added bring French press for tomorrow 6:25 a.m.
That sounds like a wrestling finisher.
It's a coffee thing.
Is it a coffee thing?
Yeah.
What is it?
Okay.
There's something interesting takes place.
We're going to do grab and go early due to the play, so if anybody wants grab and go, they need to come down now
Hey,
Oh, that's really
before the
good.
play.
I'll tell you what. Could be good day. Yeah. Okay. So yesterday we had a wonderful day. We talked about some waves. So picking up here, before I get too carried away, I want to remind you that on Friday is your quiz. You guys have me tomorrow, so good news for you. Great time, man. Besides that, I will tell you this, because I feel like you need to be aware that there is not a lot of new information that has been covered. So it's good, you get to learn a lesson early on. Once you learn it, don't forget it, all is fair game. Because here's what's going to happen. We're going to have to, how do you say, put some,
More conversions.
that's a good idea. There we go.
Lovely.
Yeah, let's get with it over here.
Yeah.
I'm talking about. You got to know how to do a mole conversion. You got to know all things. How it combines together. So make sure and be looking and studying for that.
So like, Mr. Ross, when we get to the end of the year, will I still have to go back and like look at my notes from the study to study for the test? Like end of the year. I mean, not end of the year test, but like test from towards the end of the year.
Yeah, it's for a game, man.
Okay.
So like, week 20, I can ask you, what's the top of a wave called? You're ready. Okay, so want to see if you guys can see something today. Hopefully this works out well. If it doesn't, well then Mr. Hall just bust it. Oh yeah, it works out great. Alright. If you need to move closer, feel free to move closer. But what I'm wanting you to see, do you see the dot? This is my good laser.
It's not really a dot for me, I have astigmatism.
I have astigmatism too, and it's still a dot.
It's a rhombus back here.
Why don't you wear glasses?
I haven't seen the eye doctor yet. I filled the.
Now, how in
eye
the world
test.
do you have astigmatism?
I filled the eye test on my.
It doesn't mean you have astigmatism.
No, I mean like I know I can't see light like that. Like it's really like weird shapes and stuff when I look at lights, which is normal.
So you self-diagnosed yourself with astigmatism?
I mean, yeah. I don't think it's the hardest thing in the world to diagnose.
Do you know what astigmatism is?
Something to do with light.
No, it's something to do with the eye.
Oh well, yeah. Well, your eye perceives light.
No. It is with the shape of the eye. Eye's supposed to be round like a basketball, but if you have astigmatism, it makes points like a football.
Yeah. I like, I have a
Yeah.
prosthetic eye I pop out sometimes, take a look at, study. It's pretty funny.
I love it. Alright, anyways, you see the dot? There's the cool thing. So if I run it through a wire mesh, what do you see?
Dot with lines.
With lines. Interesting. Do you see the dark bands?
Yeah.
Where's it coming from?
Wire.
So it's the wire. It gets bigger if I go over there.
Yeah.
So no, I can see it all.
Well, here's the thing. What's the property of light?
Hard to put away.
Yeah, it's both.
It's a photon.
So what's the wave part property? What do waves do?
They radiate, or, well, not radiate, it's like,
Expand.
They
disperse.
expand out. So why am I getting dark bands?
Because the light can't travel through the wire.
It's called-
But the light that goes through it should expand and fill it.
It's more concentrated to a
Oh.
finer point.
I don't know. It just wants to be different, I guess.
It just wants to be.
It's weird, lasers.
Yeah.
I'm saying it's a dot.
Yeah, you can't see it too good there.
That's a dot.
Yeah, that's a dot.
The other one was very clearly a rhombus. A red one was definitely a dog eye.
Watch your eyes.
No. Oh, God.
So why do I start with that? This starts to show you something cool. So how do we know light is a particle?
It's
Yes.
a photon.
How do we know photons exist?
Huh?
How do we know photons exist?
The photoelectric effect.
So how do we know that electromagnetic radiation is a particle?
Wasn't it like throwing off electrons or something?
Yeah. So the photoelectric effect. But why does that explain that electromagnetic radiation is a particle called a photon?
Um, um,
What's electrons?
oh, you know, like when you put the thing in a tin bed, the little things pop out.
What?
You said yesterday when you put like a little like
I-
metal in a tin bed, the little things pop out.
Yeah, I said as an example. I'm pretty sure that's not going to happen, but it's just like an example. It's like, you know, if you take a piece of metal and throw it in your microwave, it will happen.
Okay.
When you look at photons, what are photons?
Or quantitative energy with no mass.
So quantum energy with no mass. So this is what the particle of electromagnetic radiation is. Since we have photons, how can we explain that they exist? Well, the photoelectric effect is where if we shine different forms of electromagnetic radiation on a piece of metal, eventually electrons are going to shoot off of the metal. Once it hits the certain frequency of the wave. So it's not about the intensity, it's about the frequency behind it. But an electron is a negatively charged subatomic particle. If it's a negatively charged subatomic particle, what's an electron?
Negatively charged subatomic particle.
Yeah. So we classify it as a particle. Well, waves can't interfere with particles. Particles can only interfere with particles. Showing that electromagnetic radiation has to be a form of particle.
For sure.
Got me?
100%. Crystal clear.
Very important you can explain that one. Because here's the second one. What explains electromagnetic radiation? We really need to work on abbreviation of this. Is a wave. So I went ahead and I showed you like one property that helps us with this, the natural radiation expansion of light. But so there's another one that comes into play when you look at this. There's a very famous experiment. This experiment will come back up in this class. It is one of my favorite experiments to talk about. It is the famous double slit experiment. So you look at the double slit experiment, this is what it's like. I have a wall. In the said wall, I put two slits, hence double slit. Back behind it, there is a light source. What is light? It's a form of
Waves.
electromagnetic radiation. Okay, and we know that it is a wave. And what do waves naturally do?
disperse out.
No. So they're going to disperse outward. So I have some light source with an opening. So it keeps radiating out, right? Now here's the interesting thing. You have on the back wall of the room detector. So if we look at this setup, then what's going to happen? The light radiates outward, expands until it hits the wall. Then it hits right here where two slits are. Well, what's going to happen there?
It's gonna go,
Huh?
it's gonna go to.
So it'll go through. Okay. So let's look at the first slit. What happens at the first slit when the light hits it? It goes through and what? Expands. Radiates. Yes. That's simple. But then, look at the second slit. What happens at the second slit? Oh, expands also. Okay. So whenever I do this, if I look on the back wall, something very interesting takes place. I get bands of light and bands of not light. But shouldn't light, like light radiates out, shouldn't it fill in all the space? So what's happening?
This is gonna sound stupid, I like that. The lot waves are they bouncing off each other because the holes are so close together.
Probably
That
because
sounds stupid.
Probably because the frequency of the light source is different in the areas where one part of you can see, another part you can't.
So what happens here on the back wall is we see something called an interference pattern.
Yeah.
Now, interference patterns are properties. I'm not going to write it down what an interference pattern is, if you literally see it right here. It's like bands of light, no band of light. Light, no light. Light, no light. You're going to find out why we call it an interference pattern. So, the interference pattern is taking place here. This is a property of waves. So this is how you can show that light or electromagnetic radiation is a form of a wave. Now we gotta explain why this is happening. So I give two waves, different wavelengths, different frequencies, but this will get us to prove our points. So there's some certain points I want to look at on the waves. Okay. So we'll look at the blue parts. Then we'll look at the reds. So I'll go ahead and tell you, this is what's happening. Like when I took the wire mesh and I signed the laser through it, it's the same principle as the double slit. We should see those bands fill in, but we don't. And there's a reason for this, is because of this principle happening right here. David's spot on with it, that the lines and the waves are interacting with each other. So if you look at the blue spots, you'll see same points of the waves match up, which give us something called constructive interference. Now, whenever you look at construction, what happens whenever construction's taking place? If I hire some contractors to do construction for me, what are they gonna do?
They usually build something.
They're gonna build something. That's what's happening here with constructive interference. The same parts of the wave are meeting up. Building each other up, giving the bands of light. Examples of places that you can see this. So same parts of the wave. We have crest meets with a crest. Trough with trough. Now it doesn't have to be crest and crest and trough and trough. It just has to be the same points on the waves. That's why I marked these blue lines here. Blue lines here. They're not exactly the same, but they're very similar. So here's a crest and here's almost a crest. They're going to build each other up. They're not opposing each other. Then there comes typically the guy's favorite one. The red ones.
For blue,
What?
the color blue.
I get that, but these are red marks. I gotta stick with the color, man.
They break each other now.
Video's gonna look weird if I don't. Red marks. These are opposite points of the wave. If the same points build each other up, what do you think's happening on the
They're
opposite?
breaking them down.
You got that right, baby. It's demolition day. We'll rip that thing up. Woo!
Really Crips versus Bloods in there.
Really?
Well, in this case, Bloods versus Bloods. My bad. Made a mistake.
So what happens if you tear something down? It's not called construction, it's called destruction, which is why we have destructive interference. So if constructive interference is the same parts of the waves meeting up, what happens at destructive interference?
Opposite part of the wave will meet.
Look at you.
Break each other down.
So opposite parts of the wave meet up, canceling each other out, giving the bands of darkness. Points like this, that you'll see. So we're looking for opposite points, so this is where crest and trough meet. Does it have to be crest and trough? No, it just has to be the opposite points on the wave. So these are really big ideas and concepts that we get into that really mean a lot. So I need you to be able to understand, first, explaining how we know electromagnetic radiation is a wave. I introduced it to you with a natural expansion. But that's not good enough now. This right here is the big idea. We get the interference patterns from the waves interfering with each other. Well, what types of interference is happening? Why am I seeing this that I'm seeing? So explaining why the interference pattern is created. Why do I get bands of light and bands of darkness? The reason for it is I get constructive interference that builds up. That's why we get the bands of light, and the destructive interference is canceling each other out. Got me? Not only that, but you also need to be able to explain to me how you know electromagnetic radiation is a particle. That got me?
Yeah.
So this brings in a major idea, and this is what really shifted everything for us in the scientific community. What is electromagnetic radiation qualified to be? A wave or a particle?
Wave.
Well, it's a wave. Okay, very good. Wait, I thought it was a particle.
It's
That's
both.
both.
It's both. But I thought it was a wave.
It's both.
It's both. But I thought it was a particle.
It's both.
Well, you can't be both. How can you be
You
both?
said
I
it
mean,
was both.
look at light.
That's both.
How in the world does that happen? Everything in the world has been classified as a wave or a particle. Now you're just looking and saying all of a sudden it's both?
Yeah.
Yeah, pretty much.
Well, okay.
I didn't make it up, but dyslexic buddy of mine over at the science committee did. Weird fellow.
Some never go.
That's radio scientists. I think they need to scratch everything and start over. And fix some things.
So Albert Einstein proposed this then, because what came first was this. But nobody could understand or explain why light would interfere with particles. So Albert Einstein explained the photoelectric effect, and at the end of it he looks and goes, "Bruh! It's both!"
What was it?
You tell me that waves and particles are kind of like yin and yang when it comes to electromagnetic radiation.
Whoa, very good, yes. So wave particle duality states that electromagnetic radiation is a wave and a particle. So if you want to explain this, you can explain by double slit. Experiment showing wave properties. And photoelectric effect. Showing particle properties. Okay?